And our next speaker is an experimental physicist at the Advanced Technology Research Center at Mitsubishi Heavy Industries in Yokohama. He's been investigating the occurrence of nuclear reactions in deuterium permeation through a specially prepared nano-sized multi-layer palladium complex. The method he developed permits the transmutation of some elements such as cesium or barium into praseodymium or samarium with a relatively simple process of deuterium gas permeation at a pressure differential of just 1 atmosphere. Please join me in welcome Dr. Yasuhiro Iwamura.
Thank you. I'll talk about our transmutation method. Transmutation reactions induced by deuterium permeation through nanostructured palladium multilayer thin film. First, I would like to introduce my method. So, this figure shows the merits of a transmutation method. Conventional transmutation requires a large apparatus such as an accelerator and a nuclear reactor, as you know very well. In the contrary, our method, permeation-induced transmutation method. Nuclear transmutation can be induced by deuterium permeation through our original nano-structured palladium multilayer thin film. And this method requires a very low, not so high temperature and not so high pressure. We put the elements on the surface, the elements which we would like to transmute. For example, cesium and barium and other elements. And we expose this side to D2 gas. And the other side, we keep the vacuum condition. Because D2 gas and also hydrogen gas can permeate through palladium. So D2 gas permeation occurs through this nanostructured multilayer thin film. And after that, this element can be transmuted to another element. This is a feature of our method. And this figure shows the reactions, nuclear transmutation reactions so far in Mitsubishi Heavy Industries, LENR. For example, cesium to praseodymium, and strontium to molybdenum, and barium to samarium, calcium into titanium, and recently observed tungsten into osmium or platinum. And based on these experimental observations, we can see that the uncolor metals seems to be easy transmute by our method. And also, we have some rules for the original element and the transmuted element. In this case, in cesium case, atomic number increased 4 and the mass number increased 8. Very unconventional transmutation. And also, in this case, cesium plus 4D get the praseodymium, and in the barium case, 60, and we get the samarium, and calcium case is 2D. So, according to the experimental results, 2D and 4D and 60 reactions are observed. It's, as you know well, 2D equal alpha particle, so it's just like alpha capture reactions. But this is just a phenomenological observation based on our experimental results. Okay, and This figure shows potential applications for this technology or phenomenon. We would like to use this phenomenon for nuclear transmutation of radioactive waste. This figure shows image, application image for radioactive waste. If we apply this technology to the 1 gigawatt nuclear power plant and we transmute cesium-137, we need this size based on the results. And the other application is production of rare earths using for example, using the tungsten, we get the platinum. And also, we will be able to use portable nuclear energy cells. All the observed and transmutation reactions are exothermic reactions. So we get the energy, we get the heat by our experiment. So it will be possible using the energy source. Okay, so we'd like to explain about the experimental method. This chart shows the fabrication of nano-structured palladium multilayer thin film. At first, we washed the palladium sample 24 millimeter by 24 millimeter, and the thickness is 0.1 millimeter. Washing the palladium sample with acetone to remove the organic impurity, and after that we anneal the sample under vacuum conditions at 900 degrees centigrade for 10 hours. And we wash the sample with aquaregia to remove the surface impurity after anneal. Aquaregia is a combination of HCl and HNO3. And after that, we perform 5 times alternate degree sputtering of calcium oxide and palladium, and we put the palladium surface by argon ion beam sputtering method. Okay, and this figure, photograph shows the experimental apparatus with XPS. We put the sample with cesium in the chamber, and we measure by the XPS. XPS is X-ray photoelectron spectrometry. This is the original apparatus. Okay, and this is the example of transmutation of cesium into praseodymium. At the beginning of the permeation, we have only cesium only, and we have no praseodymium. But due to gas permeate, gradually cesium decrease, and correspondingly praseodymium increase. So we understand in this experiment, cesium transmute into praseodymium. And as I said, in this case, atomic number increased 4 and mass number increased 8. But if we omit cesium or deuterium or calcium oxide, we do not observe this transmutation. Oh, sorry. Okay. This is the results of control experiment. If we use hydrogen instead of deuterium, we cannot see any change of cesium, and also we cannot see any praseodymium. And if we omit cesium, we also cannot see any change. And if we omit this calcium oxide, also we cannot see any change. So we can say that deuterium and multilayer thin film and elements such as cesium is required, necessary to observe this phenomenon. Next experiment, we put the barium instead of cesium. In this case, we get the samarium. This is a result of XPS analysis. We get a very clear samarium spectrum. And this figure shows the mass number correlation between barium and samarium. We perform two types of experiments. One is a natural barium transmutation experiments, and the other is enriched barium experiments. Natural barium have an isotopic distribution like this. 138 is a major element, a major isotope. And if we put natural barium on the surface, and we will get the samarium, as I showed the previous slides. And we analyze the mass distribution. And blue one is background. Background means a sample with barium, but not permeated one. This red one is a permeated sample, after permeated sample. We can see the significance increase of mass number 150 for this case. But if we put the 137 barium before on the surface, and after permeation, we get the mass number 149 increase in this case. So these two experiments have the same rule. In this case, atomic number increased 6 and the mass number increased 12. And also in this case, same rules exist for barium and samarium experiments. Okay, so we will go to the next point. To increase the credibility, reliability of measurement, we use another analysis method, an in-situ measurement we try with the other researchers in Japan. RIKEN is a National Institute of Physical Chemical, the National Institute. So this is a photo of in-situ experiment setup. We carry this apparatus to the spring gate. Spring gate is very strong, one of the largest synchrotron radiation facilities, and we can use a very strong synchrotron orbital radiation X-ray in this facility. And spring gate is operated by RIKEN. And we use synchrotron orbital X-ray here, and we put the sample here, and detector is here. And so we can measure by this apparatus using the XRF, X-ray fluorescence spectrometry. XRF is a very established analysis method. So we use this facility. This figure shows the in-situ measurement setup at spring gate. As I said, synchrotron orbital X-ray comes here, and here we have a palladium complex with cesium, and this chamber is filled with D2 gas, and the D2 gas is permeated like this, through this. And we can get the fluorescence X-ray on the surface, and we have a detector here. This is the results of confirmation of precipitation. by in-situ measurement. This is X-ray fluorescence energy and count. This white one corresponds to the initial state before permeation, and black one corresponds to the after permeation. We can see that after permeation, we can see the praseodymium X-ray fluorescence increase. So at this point, transmutation reaction of cesium into praseodymium occurred. And this reaction were confirmed by the researcher in Mitsubishi Heavy Industries and other university researchers. Okay, so I will explain about the surface distribution and depth distribution of praseodymium. This is the experimental setup for surface distribution of praseodymium. We use 5.97 keV synchrotron radiation X-ray, and we use a slit, and we get the microbeam. And we put the sample on the XY stage, and if we move this stage, we can measure the surface distribution of praseodymium. This is the result of detection of praseodymium. This figure shows the surface image for the sample. And this red line, red region have very much praseodymium detection. This is the XLS spectrum. This red one is correspond to here and here. And we can see that the very clear praseodymium. And the yellow region, we have some praseodymium. But the other region, we do not see any praseodymium. So we can see that praseodymium is very localized. And if we use a further smaller beam analysis, we analyze this very large praseodymium region by more smaller X-ray. And also we detected a more localized praseodymium distribution. So it might suggest the existence of hotspots or for transmutation, maybe. And this view graph shows the depth profile of cesium and praseodymium by XPF. And before permeation, this is the sputter time, and this is the atomic ratio to palladium. And this axis corresponds to the depth. So before permeation, cesium distribute like this because we use cesium ion implantation to provide the cesium on the multilayer thin film. And after D2 gas permeation, surface region about 10 nanometer, cesium decrease, and praseodymium increase like this. So we can see that the nuclear transmutation reactions occur near surface by this results. And next point is the role of calcium oxide. As I said, we use a multilayer thin film containing the calcium oxide. So we explore, investigate the role of calcium oxide now. And this is the facility, D+ ion bombardment experiment performed at Tohoku University. D+ ion bombardment on metal target. If we bombard metal, D gets some D's around here, and we get the normal DD reactions, and we can estimate the deuterium density. And this is the results of deuterium density measured by D+ ion bombardment. This axis means the deuterium density estimated by the normal DD reactions. This is a normal palladium, and this point is correspond to palladium calcium oxide. So it suggests that the density of palladium complex indicated one order larger than normal palladium. So our multilayer thin film seems to have a much deuterium in the surface. Okay. So, and the next point is the effect of intermediate layer. Usually we use a calcium oxide. If we replace the calcium oxide, if we use a magnesium oxide instead of calcium oxide, we tried 3 times, but we did not no praseodymium. But if we use Y2O3, we detected praseodymium many times. And work function of the magnesium oxide is 3.3 electron volt, and calcium oxide is very lower work function, and Y2O3 also have a low work function. These materials are very easy to emit electrons. So work function of the intermediate layer seems to be very important. So now, if we have an intermediate layer that have a very electron emitter, we would have electron-rich state on the surface of the palladium sample. So we now have the assumption electron-rich state is important. Okay. So this is a preliminary recent results of transmutation of tungsten into platinum or osmium. This is an experimental procedure of tungsten experiment. At first, we fabricate the palladium multilayer thin film, and after that, we perform the tungsten ion implantation. And we perform the D2 gas permeation experiments like this. This is the results of transmutation of tungsten into platinum or osmium, and by SIMS as secondary ion mass spectrometer. And in this figure, this is the mass number and the count, SIMS counts, and the cross means a non-permeated sample, and triangle and rectangular one, the permeated sample 1 and 2. And we can see that the mass number 90 increase after permeation, because we cannot see any mass number 90 here. And of course we have tungsten, and also we have impurity platinum. But platinum is here, and mass number 190 platinum should be 0.01%. So we cannot see at the mass number 190. Also, we cannot see mass number 189 for osmium. Osmium, so we can see that we have no osmium in this sample. So this increase for mass number 190 could be might be attributed to the generation of platinum 190 or osmium 90. But it is necessary to confirm these results by other experiment, for example, XRF or XPS, other elemental analysis. We will, and it's a next work, I think. Okay, so I would like to introduce our activity to get the commercial device for commercialization. It is necessary to increase products because praseodymium we observed is a range of a nanogram order. Nanogram order is not so large, so we should increase products. So we use an electrochemical method for increasing the products. We are now trying to increase that. This figure shows the praseodymium dependence on D2 gas pressure. This is the amount of praseodymium nanogram and the conversion rate here. Conversion rate is half portion of cesium transmuted into praseodymium. And the blue point means low pressure, and red points high pressure results. And low pressure is 1.2 and 1.3 kilopascal atom, and high pressure is 1.8 to 2.3 atoms. And we can see that if we increase the pressure, we get more praseodymium. So D2 pressure is very important for increase the amount of element amount of praseodymium. So we try to increase the praseodymium using the electrochemical method, because if we use this kind of configuration, we can control the deuterium density on the surface by the voltage, applied voltage. So if we apply a very large voltage, we will get a high deuterium density on the surface. So we use this kind of apparatus, and we are now performing many kinds of experiments. This is a figure of a procedure of experiment. At first, fabrication and the cesium ion plantation is performed. And after that, permeation by electrochemical method. This is an example of Sims analysis after permeation. This is the mass number, and this is the Sims count. And our sample is divided to a permeated region and the not permeated region. The center of the sample is D2 depermeated, and the corner the not permeated. And also in this figure, we plot the results of no implantation case, no cesium case as a reference. And we can see that the cesium mass number 133 at the corner is the largest, and the decrease on the permeated region like this. But around mass number 140, we can see the increase around mass number 40, red region. So for permeated area, and this one is enlarged spectrum for along the mass number 40. We can see that the only permeated region, we have some mass number 140 and 39 and 41, and the other reference and the corner we cannot see if we use a linear scale. So we have a match amount of mass number for permeated region. And to confirm this result, we performed the ICP-MS analysis. ICP, inductively coupled plasma mass spectrometry, to confirm this result, because the SIMS is a meta-analysis for point. So if we analyze this sample, also we get the similar results. We can see the decrease of cesium-133 and increase around the mass number 140 for surface analysis. Okay. And this is an enlarged spectrum for around 140. We have mass increase 139, 40, and 41, and 42. A very similar result. So we can see that the SIMS, point and ICP-MS, all surface analysis gave similar results. And also we noticed that in the case of D2 gas experiment, we only have praseodymium only, but in this case we have another mass number. So it is the different tendency from D2 gas propagation. Now we are trying using this method. Okay. And also, in this case, we only have a mass spectrum analysis only, so we should we make consideration on compound species. So possible compounds for mass number 140 and mass number 139. These are the possible compounds. But these compounds, we investigate very carefully that are not explained consistently by these compounds for this spectrum. Okay. So lastly, I would like to replication experiments. This figure shows replication at the Toyota Central R&D Laboratory. They present these results at the conference, ICCF conference, held August this year in Korea. They fabricate very similar multilayer thin film and very similar way to replication experiments. This is a sample, and this region filled with D2 gas. But in their case, they use a very high 9 atoms atmosphere they use, and they analysis the sample after permeation. And this is the results of replication. This is the sample number, and this one is the cesium concentration and the praseodymium concentration here. If they omit no cesium, they cannot, they could not, no praseodymium like this. And if they, in their case, these data are ion implantation case, they get this one is a cesium and this one is a praseodymium. So they got the praseodymium like this. But the amount of praseodymium is 10 to 12 atoms per square centimeter. So it is a few nanograms, so they have not so much praseodymium, but they replicate our results like this. And also other researchers in the University of Osaka and University of Iwate also replicated our results. Okay, so I'd like to conclude my presentation. Low energy nuclear transmutations from cesium into praseodymium, barium into samarium, and tungsten into platinum or osmium have been observed in the palladium complexes, which are composed of palladium and calcium oxide thin film and palladium substrate induced by D2 gas formation. Experimental data that indicates the presence of transmutation have been accumulated, and experimental conditions for inducing low energy transmutation reactions are gradually becoming clear. Although systematic experimental study is still insufficient. Liquefaction experiments have been performed by some researchers, and similar results have been obtained. Potential application would be expected for innovative nuclear transmutation method for radioactive waste and a new energy source. Thank you for attention.
And we'll take questions. And Ed, I introduce you.
Yeah, Edward Biden, Aerospace Corporation. First of all, I'd like to congratulate you on a very interesting talk. I was sitting down, jotting down questions to ask you, and all of them but one you answered during your talk. So it was, I think that's rare. The question you didn't answer is: have you ever tried protium with nickel or light hydrogen on nickel?
Light hydrogen experiments. Oh,
On nickel.
I've never tried to that. I also have interested in the nickel and hydrogen system, because nickel and hydrogen is very cheap. So I have a very interested in, but I have no time and no money for.
Do you have plans of doing that?
Yeah. At present, we have a rigid plan for nickel and hydrogen experiment, but I'd like to try.
Other than Toyota and Mitsubishi, are there other people in Japan pursuing these experiments?
Yeah, Mitsubishi and Toyota R&D Center, and the researcher of Iwate University, and other company. The other researchers, Toyota Motors researchers, also have interest and some experiments, and other companies they did not present their results, but underground they performed very similar experiments, I heard.
And the primary interest of Mitsubishi is for transmutation of hot elements from reactors in order to...
Yeah, mainly we have a nuclear power plant section, so radioactive waste is our commercial aim, yes.
And do you feel like you're getting close to being able to make this a practical application using the electrochemical method?
If we increase our amount of products, it will be possible, I think. And gradually we are improving, so it would be possible, I think, in my field.
Thank you.
Other questions? Please.
My name is David Bradley with Bradley Engineering. And I was just curious, since there are so many upside potential applications, why do you suppose there's a lack of funding on an industrial scale?
Yeah, why lack of funding? Because this field have so please explain.
Some context. This is very unusual work. This is work that A lot of people don't know about, and B, it represents a paradigm shift. This is very unexpected. People, except for those of you who come and listen and get the information, don't believe it. And so there's a conceptual barrier to it. And there's also been, I don't hold my punches, as Ed mentioned. There's also been a lot of silliness in the field, and that silliness has a tendency to give the field, to cause the field to lack the respect that some of the better science deserves.
In your expectation of further work, do you see that there is a process and an endpoint that would involve starting with cesium-137 and then getting to something with either a very short half-life or something that's stable? I mean, is there something where you can just add up alpha particles into something that's okay?
Okay. You mentioned about the chain reaction, or
No, I mean, just
stable?
as far as, you're working with cesium-133 right now. Do you expect that there's a something where you could put in cesium-137 and get to a stable endpoint?
Yeah. We will get the stable elements if we use cesium-137, because preliminary experiment we perform, and we get the decrease of the gamma ray from 137. So in this case, mainly we get the stable state of element.
So you believe that there will be a system where you can put cesium-137 in and you can anticipate what the end product will be?
Maybe European program.
Because you can do things with cesium-137, you will get people's attention.
More questions? Very well. Let's thank our speaker again.
Thank you.